So hello everyone, in the last class we looked into how bridges can forward the message from one local area network to another local area network, and for this we also came to a conclusion that bridges must be equipped with a routing capability, because when a bridge receives a frame it must be able to decide whether or not to forward the frame or not, because if a bridge is attached to two or more networks, it must decide whether or not to forward the frame, and if it wants to forward, then on which LAN it should forward. So it should be equipped with the routing capability. Alright, so going ahead now, coming to a new concept which is called as the spanning tree approach. Alright, now in this case the spanning tree approach is a mechanism in which bridges automatically develop a routing table. So this is a mechanism in which the bridges automatically develop a routing table and update the table in response to the changing topology. So what happens if the topology changes, or if some link has some disturbance, or it stops working and the topology changes, then the bridges update their routing table accordingly. The algorithm consists of the three mechanisms. So the three mechanisms, this algorithm, spanning tree algorithm, it consists of the three mechanisms. The first one is the frame forwarding, second one is the address learning, and the third one is the loop resolution. We are going to talk about these three mechanisms in detail. So let's first of all talk about what is frame forwarding, then we will talk about what is address learning, and the last one we will talk about loop resolution. So let's start with the frame forwarding first of all. So let's understand what is frame forwarding. It maintains a forwarding database for each of the port. So a forwarding database, that means when a frame is received, to which LAN or to which bridge the frame must be forwarded, that is called as the forwarding database for each port. So in this scheme, a bridge maintains a forwarding database for each port attached to the LAN, and the forwarding database indicates the address of the station for which the frame should be forwarded and through which port. We can interpret for example, let's understand some diagram over here, the previous diagram. Now another point to note over here is, for each port a list of stations is also maintained. A station is on the list if it is on the same side of the bridge as the port. Alright, so let's go back to the example which we did in the last class, this example. So for example over here, for the bridge 102, this is bridge 102. Now for this bridge bridge 102, the stations on the LANs C, F and G, stations on the LANs C, F and G. So they are on the same side of the bridge as the LAN C port. So the LAN C port is here and they are on the same side of the bridge. And the stations A, B, D and E, they are on the same side of the bridge as the LAN A port. So when frame is received on any port, bridge must decide whether the frame is to be forwarded through that bridge and out through one of the bridge's other port. So for example, let's understand one example from here. Let's understand first of all what is the port. So if you see, the bridge has two ports. On one port it is attached to LAN A, and on other port it is attached to LAN C. That's why I said LAN C, LAN F and LAN G are on the same side of the port as LAN C, whereas LAN A, LAN B, LAN D and LAN E, they are on the same side of the bridge on the port of LAN A. Now let's understand, when a frame is received on any port, the bridge has to decide whether the frame is forwarded through the bridge and out on bridge another port. So for example, if a station 3 wants to forward a bridge, wants to forward a frame to LAN F or to station 6, so it will be sent to bridge 102 on one port, which is this port, and that frame will leave from bridge 2 on this port. So outgoing port and ingoing port. Now suppose that a bridge receives a MAC frame on the port X Let's assume that this is port X. So bridge receives a MAC frame on the port X. So now the following rules will be applied. So what this bridge will do, it will search its forwarding database to determine if the MAC address is listed for any port except for port X. So it will just check that if the MAC address is there in the forwarding database except for the port X on which it has received the MAC frame. Now, if the destination MAC address is not found, in its database, what it will do, it will forward the frame out all ports except the one from which it received. So what it will do, it will forward the frame to all the ports. Maybe it is attached to more ports also. So what it will do, it will forward the frame on this port, but it will not forward the frame on the port from where it received. This is a part of the learning process which will be described later. Now, if the destination address is found in the forwarding database, so the second point, the previous point that I discussed was if the MAC address is not found in the forwarding database, then it will forward it to the next port, some outgoing port. But if the destination address is found in the forwarding database for some port Y, then it will determine whether the port Y is in blocking or forwarding states. And sometimes a port may be blocked, which prevents that port from receiving and transmitting the frames. Now, if port Y is not blocked, it will transmit the frame through port Y on the LAN to which the port attaches. So this is how address forwarding is done. So it will search the forwarding database if MAC address is listed for any port. If address not found, forward to all ports except X. If address listed for port Y, check port Y for blocking or forwarding state. If not blocked, then transmit the frame through port Y. Now next we talk about the next phase of the spanning tree algorithm, which is address learning. So how it learns the address, let's talk about this. Now let's understand how a bridge learns the addresses. So when a frame arrives on a particular port, for example, let's assume that a frame arrives on a port X. So it has come from the LAN attached to the port X. So the LAN which is attached on the port X, the frame has arrived from there. So clearly has arrived from the direction of the incoming LAN. So the source address field of the frame indicates the source station, and in the frame the source address field will indicate the address of the sender. So bridge can update its forwarding database that for that port on the basis of sender field for each incoming frame. Now to allow for changes in the topology, each element in the database is equipped with the timer. So there is a timer attached, each have a timer on each entry in the database. So if the timer expires, then the element is removed from the database because the corresponding direction information may no longer be valid, or maybe the topology has changed, or maybe the link has expired, or maybe there is a problem in a link. So each time a frame is received, the source address, the sender's address is checked in the database. If the element is already in the database, entry is updated and the timer is reset. If the element is not in the database, new entry will be created and with a timer, and the timer is set for that new entry. So that is how address learning mechanism works. Now the last mechanism which we are going to talk about is the looping. Now there is a problem with the address learning. The address learning works for a tree layout. That means if for example, for a certain topology, a tree can be formed, some tree-like structure can be formed, the spanning tree algorithm will work for that. That means if there are no alternate routes in a network, alternate routes means there is no closed loop. So the address learning mechanism which we have discussed now is effective if the topology of the internet is a tree. That means there are no alternate routes. The existence of the alternate route means that there is a closed loop. Now for example, if I go back to my previous example over here, This is not a tree topology because there are alternative routes over here. For example, there are alternate routes. That means there is a closed loop. For example, LAN A bridge 101, LAN B bridge 104, and LAN E bridge 107. So, for example, if you see over here, bridge 101 on LAN A, bridge 101 on LAN A and LAN B, bridge 104 on LAN E, and bridge 107 on LAN A. They form a closed loop because, for example, if station 1 wants to send a data to station 4, there exists a path. Either it can send to bridge 101, then to LAN B, then to bridge 103, or to station 4, or directly it can use bridge 107 if it wants to send to station 5, for example. Send to bridge 107 and then directly to station 5. So there exists a alternative route. So this is not a tree-like structure. So address learning works well if our structure is a tree-like structure, but if there are alternate routes, that means a closed loop is formed, it will not work well. Alright, let's understand this problem. For example, if I go to the next slide, for example, over here, let's understand what is the problem of the closed loop over here. So, I have two bridges alpha and beta, and there are two LANs and two stations, LAN X and LAN Y. Station A is attached on LAN X and station B is attached on LAN Y. So, for example, let's assume that at time t is equals to 0, station A transmits a frame addressed to station B. So, station A transmits a frame addressed to station B. So, in this case, the frame will be captured by both the bridges alpha and bridge beta. So each bridge will update its database that station A is on LAN X, and then it will transfer the frame to station B or on LAN Y. Let's assume that bridge alpha transmits the frame at time t is equals to t1, and bridge beta transmits the same frame at time t is equals to t2 later on. So now B will receive two copies of the frame. Also, each bridge will receive others transmission on LAN Y, and each transmission is a frame with sender's address A and a destination address B. So each bridge will update its database to indicate that station A is in the direction of LAN Y. So neither bridge is now capable of forwarding a frame addressed to the station A. So this is what is the problem over here. So for any connected graph, there is a spanning tree maintaining connectivity, and no closed loops, and algorithm should be dynamic. So to overcome this problem, a simple result from the graph theory is used. So what happens is, we need to have a connected graph which consists of a nodes. Nodes are nothing but the stations, and the edges are the transmission links connecting the pair of nodes. So there is a spanning tree of edges that maintains the connectivity of the graph, and there is no closed loops. So in terms of internet, each LAN corresponds to a graph node, and each bridge corresponds to a graph edge of the graph. So if I go back to my previous slide over here, our previous example. Now in this case, if we remove any one of the bridge, whether 107, 101 and 104, we will get a spanning tree. So what we need is to develop a simple algorithm by which the bridges of the internet, they can exchange sufficient amount of information automatically and derive a spanning tree, and the algorithm must be a dynamic one. Dynamic means it should be a unique one. Algorithm should be a dynamic one. Dynamic means when the topology changes occurs, the bridge must be able to discover this fact automatically and should be able to construct a new spanning tree. This is called as that the algorithm should be dynamic. Now, according to the spanning tree algorithm developed by IEEE 802.1, what are the features or what is required? First thing is, each bridge should have a unique identifier, like no two bridges should have the same name, or you can say the same identifier. And cost should be assigned to each bridge port. Cost should be assigned to each bridge port. So in absence of any special consideration, all cost can be set to equal, and this produces a minimum hop tree. Also, the algorithm should involve a brief exchange of information between the bridges to find a spanning tree. So to discover a minimum cost spanning tree. And whenever there is a change in the topology, bridges should automatically recalculate or update the spanning tree. So these are the 4 features of the IEEE 802.1 spanning tree algorithm. Alright, so moving ahead, let's talk about another connecting device, which is a hub. We have learned hub is used in the star network. So it's an active central element of a star layout. We have discussed about it when we discussed about the star topology. So earlier the term hub was used to a star topology LAN. Each station is connected to a hub by 2 UTP lines. One is transmission line and another one is the receiving line. So each station is connected to a hub by 2 lines, transmitting line and receiving line. Hub can also act as a repeater. So when a single station transmits, the hub repeats the signal on the outgoing line to each station. Also, ordinarily, the line consists of 2 UTP pairs and it is limited to about 100 meter by UTP properties. It consists of 2 UTP pairs. Because of the high data rate and the poor transmission qualities of the shielded UTP cables, the length of the line is limited to about 100 meters. So because of the high data rate and because transmission quality of UTP cable is very poor, so the line of the wire is limited to 100 meter. But as an alternative, optical fiber cable can be used, and in this case the maximum length can be made up to 500 meters. Also, we should note that the scheme is physically a star, but it is logically a bus. So a transmission from any one station is received by all other stations, and if 2 stations transmit at the same time, there will be a collision. Although it looks like a star, but actually logically it is a bus topology, because it is actually a broadcasting. So whenever a station sends a data to some other station, that data will be received by all the other stations, and if 2 sources or 2 systems or 2 nodes try to send the data at the same time, there will be a collision. Now let's talk about bus, hub and switches. So let's talk about hub, bus and switches. In the bus configuration, all the stations share the capacity of the bus. So whatever is the capacity of the bus, let's assume that it is 10 kbps or 10 mbps, it will be shared by all the devices. So if there are, for example, 10 devices on the bus, it will be shared by all, but only one station will be transmitting at a time. So in this case, only one station will be transmitting at a time. Whereas a hub, often in a building, it is used often in a building wiring closet, and it uses a star wiring arrangement to attach stations to a hub. And in this arrangement, a transmission from any one station is received by the hub, and it is retransmitted on all the outgoing lines. So to avoid collision, only one station can transmit at a time. Also, the total capacity of the LAN is 10 Mbps. Hub has many disadvantages over the simple bus arrangement. It exploits the standard building practices in the layout of the cable. Also, hub can be configured to recognize if there is some error in a station that is jamming the network, and to cut out the station from the network. But we can achieve a greater performance with a layer 2 switch. So in this case, the central hub acts as a switch, much as a packet switch or a circuit switch, and with a layer 2 switch, incoming frame from a particular station is switched to the appropriate output line to be delivered to the intended destination, and at the same time other unused lines can be used for switching other traffic. So it can transmit multiple frames between the separate ports, and it multiplies the capacity of the LAN. So let's talk about over here the shared medium and bus and the hub. Alright, so let's talk about bus and the hub, and the third diagram is where the hub acts as a central switch. Alright, so in this diagram, the first diagram, it shows a bus layout of a traditional 10 Mbps LAN. So it's a shared bus of 10 Mbps LAN. A bus is installed and is laid out so that all the devices to be attached are in a reasonable closeness to the point of the bus. So in this figure, let's assume that station B is transmitting. So the transmission goes from B across the lead from B to the bus, along the bus in both the directions. So the transmission goes from B, from this wire to the shared bus in both the directions, and along the access lines of each of the other attached station. So all the stations must share the total capacity of the bus, which is 10 Mbps. Now let's assume that over here the second figure is shows the operation of the hub. Here again, if you see over here, we have a capacity of the hub which is again up to 10 Mbps, and all the stations are attached to this central hub. So again in this case, station B is transmitting, and the transmission goes from B across the transmit line from B to hub. So it goes from B to the hub, and from the hub along the receive lines for each of the stations, and from the hub it goes to the receiving lines for each of the stations. The last example shows an example of a switch. So now this hub acts as a layer 2 switch. In this case also, B is transmitting a frame to A, and B is transmitting a frame to A, and at the same time C is transmitting a frame to D. So in this example, the current throughput of the LAN is 20 Mbps, although each individual device is limited to 10 Mbps. So in this case, layer 2 switch increases the capacity or the throughput of the LAN. So let's talk about the layer 2 switch benefits. So the first benefit is no change is required to the software or the hardware of the attached devices to convert bus LAN or hub LAN to a switch LAN. So no change is required. In the case of the Ethernet LAN, each attached device continues to use the Ethernet medium. Second is, each attached device has a dedicated capacity equal to the capacity of the entire LAN. So assuming that the layer 2 switch has a sufficient capacity to keep up with all the attached devices. So for example, if I talk about the figure, the layer 2 can switch a throughput of 20 Mbps, the previous example. Each attached device appears to have a dedicated capacity of receiving or transmission of 10 Mbps. Third is, it can be expanded easily. Layer 2 switch can be scaled easily. Additional devices can be attached to the layer 2 switch by increasing the capacity of the layer 2 switch correspondingly. So it's again, scalability is easier. Now let's talk about the two types of the layer 2 switch. The first one is the store and forward switch, and the second one is the cut through switch. So store and forward switch, this is a layer 2 switch. It can accept a frame on an input line stores it inside and then routes it to the appropriate output line. So it buffers briefly, it stores it and then routes to the destination port. There can be a delay between the sender and the receiver, but it boosts the overall integrity. Next is the cut through switch. This layer takes the advantage of the fact that the destination address appears at the beginning of the MAC frame, and this switch begins repeating the incoming frame on the appropriate output line as soon as the layer 2 switch recognizes the destination address. So it gives us the highest possible throughput, but there is a risk of propagating bad frames because the switch may not be able to check the errors before retransmission. So it may be able, the store in, it is not able to check the CRC. Alright, moving ahead. So let's now understand the difference between layer 2 switch and a bridge. Alright, a layer 2 switch can be viewed as a full duplex version of the hub. It can also have some logic that allows it to function as the multi-port bridge. But there are certain differences between the layer 2 switch and the bridge. So what are the differences? Let's just check it out. Bridge. The frame handling is done in the software. So there is a software for handling the frame, whereas there is a hardware for handling the same type of the frame. So a layer 2 switch performs the address recognition functions in the hardware. So the first difference is the frame handling is done by the software, whereas the frame handling or processing is done by the hardware. Second thing is a bridge can typically analyze and forward one frame at a time, whereas a switch can handle multiple frames at a time. So multiple frames can be handled by the switch at a particular time. And the last difference is bridge works as a store and forward operation, whereas layer 2 switch we can have cut through instead of store and forward operation. Now because layer 2 switch offers higher performance and it can also offer the functionalities of the bridge, so that's why bridge has suffered a lot commercially. New installations or the new LAN installations, they include layer 2 switch with the bridge functionality rather than including the bridges. So that's all I think about this chapter, and thank you so much.